In this video, we're going to be solving this circuit using node voltage analysis. That means we're going to find the voltage of each node compared to some common reference point. So again, think sea level. So if you said that Denver was a mile high, it's actually a mile above sea level, where sea level is our reference. And then that mile would be that voltage, or in this case, altitude. Once we find the node voltages in this circuit, we'll use those to determine the current Ix, which is right here. So let's get started. So the first step in node voltage analysis is to identify the nodes. So if you're a little rusty, remember you can always trace the wires. So you can do that. I'll get a highlighter this time just to do it a little easier. So you can trace the wires. So that entire wire there is a node. But more conveniently, what we'll do is we will label the junctions. So like that's a dot. And you see we already called this 1. If you wanted to, you could call it V1. And then there's another one here. So if you wanted to, again, if you don't have a highlighter, you could draw around it. But again, it's more convenient just to use a dot, and this would be V2. And then there's another junction here. And again, we would use a dot, and we would call this V3. And then down here, we have another node. And this has been labeled as our ground. And a lot of times our ground is thought of as V0. And we typically think of that as 0 volts. So that's our baseline. We compare everything to that ground. If you don't have a ground defined in your problem, you'll have to just choose one of these. So in this case, we have 4 options. We could use this node, this node, this node, or this node at the bottom. And it doesn't matter. Let me get this to... There you go. That's a little better. If you don't know which one it is, then find a source. So for instance, on this source, we know that this node down here is of lower potential. For this source, we know that this node is of lower potential. So either this one or this one would make sense based on the sources around it. Since this is an independent source, it makes sense to choose this one over this one. All right, so once we have them labeled, we have them identified and labeled, then we want to apply KCL at each of the nodes. So as a refresher, KCL, and we're going to do this one at, so I might say at 1 or at V1. And this is going to be I in equal to I out. Now, when you first get started, it makes sense to label your current directions. So I already have this current going into V1. I have this current leaving. And this one I can do whatever I want with. So the current basically through this 4 ohm over to V3 is up to me. So for the time being, I'm just going to assume that it leaves. It doesn't really matter. You get to choose. And as long as you follow passive sign convention with your polarities, you'll be fine. So in this case, we have 3 amps entering. And then leaving, I have IX. And I have this current here, which for the time being, I'm going to call I through the 4 ohm. But as we do more of these, you're going to see I'm not going to do that. I'm just going to jump straight to a different substitution for these. Now these I's we can sub out using Ohm's law. Because we really don't want currents here. The whole point of node voltage analysis is to have a bunch of equations in terms of our node voltages. So our variables in this problem should be V1, V2, and V3. Those should be the only 3 that we have. Because we have 3 different variables, we're likely going to have 3 different equations, 3 unknowns. We do technically have this as an unknown, but we assume that this is 0. So Ohm's law, say for this 4 ohm resistor, so I have I 4 ohm. So if you remember, this is V equals IR, but I want to rewrite this such that I is V over R. Because that's what I want. I want to sub out the current I. So I 4 ohm is the voltage. So this is the voltage. And so notice the arrow. It is from V1 to V2. If you did passive sign convention over here, you'd have a plus minus. So this is the voltage from 1 to 3, or realistically, it's the voltage of 1 compared to 3. And over the resistance, which is 4 ohms, you expand that, and you can do it here or you can expand it later. So if you want to expand it now, it would be V1 minus V3 over 4. And that's what you'll sub in up here. And we'll do it again for the IX, because I don't want IX either. IX is a variable that we'll find later once we find the node voltages. So IX, same idea. It is the voltage from 1 to 2. Again, notice the direction. It goes from 1 to 2. So it's V1, 2. Sorry, I almost wrote an I there. And it is over a 2 ohm resistor. So we'll sub both of those in to our equation here. So we'll have 3 equal to V1, 2 over 2 plus, and I'm just going to go back to V1, 3 over 4. And then what you want to do with this is we don't want to have these denominators down here. So our common denominator, our largest one here, is a 4. So we'll multiply everything by 4 to make that go away. So we'll end up with a 12. Let me scoop this up for you. You end up with a 12 on this side, and then a 4 over 2, so you have 2. And this is when I would generally expand this, so I'll just call it V1, 2 for now. And this is V1, 3. And then the next step would be to clean it up one more time. We would expand this, so I'd have 2V1 minus 2V2. And that is this term expanding, and I'm distributing that too. And then plus V1 minus V3. And that is me taking this term and distributing it and splitting it apart. All right, so this is equation 1. So I need 2 more of those before I can finish this. So we're going to go a little faster for these next 2. So I've already done a KCL at V1, so I'll just move over and do a KCL at V2. All right, and this is I in equal to I out. So going in, I have this IX, but again, I don't want to call it IX, so I'm just going to go ahead and call this the voltage. So again, if you want to, go ahead and label your directions. It'll help you at the beginning. A hint is if you have a ground, make your currents go towards the ground. Otherwise, you're going to get some weird negatives. You'll be able to handle it, but it can just make things a little difficult. So we'll just label it. As you get more experience with this, you actually don't have to label these current directions, but once you get started, it's a good idea to do that. I don't know why this is having trouble focusing, but it is. All right. So going in, I have the voltage from 1 to 2 over 2. So that's the IX. Both of these leave. So this is the voltage from 2 to 3. And it is over an 8. So you'll see how this gets a little bit faster. This is the voltage from 2 to 0. And that is over a 4. And so this 0 is going to drop off over here. Our common is an 8. So we'll multiply everything by 8 to get rid of our denominators. So I'll get 4V1, 2 equal to V2, 3 plus 2V2, 0. All right. And then we'll expand this. So 4V1 minus 4V2, V2 minus V3 plus 2V2. And then if I keep going, I'm going to get minus 2 times V0 and 0. So I'll do it real quick. So minus 2V of 0. But this is 0 because that V0 is assumed to be 0. And so this is equation 2 up here. All right, and then so that's now we have 2 equations. And again, I have 3 unknowns. My unknowns are V1, V2, V3. So let's do one more of these. So KCL at V3. So current in equals current out. It is nice if you write that, just to remind yourself what you're doing. And also, it's really good to note where you're doing your KCLs, so it's easier for me to follow, also easier for you to follow. So I already have all of these currents labeled from previous. So we'll just reuse them. It actually doesn't matter if you change these. So these current directions that you just kind of label, if you change their direction mid-flight, it won't really matter. This one you can't change, so don't mess with the ones that are already pre-labeled. But if you just kind of label it yourself, if you happen to change the direction later on, it generally won't matter. So coming in, we have the voltage from 1 to 3, and that is going to be through a 4 ohm resistor. This is coming in, this is the voltage from 2 to 3 over an 8 ohm resistor, and then going out is this 2 times Ix. And I know we didn't want Ix in there, but we already know that Ix is V12 over 2, so we'll sub that in. So V13 over 4 plus V23 over 8 equal to 2 times quantity, V12 over 2. So it's just a lot of the same stuff over and over. Our common denominator is an 8. So we'll get 2V13 plus V23 equal to, and so this is a 2 over 2, so it just becomes 8V12. And you expand it, so you get 2V1 minus 2V3 plus V2 minus V3 equal to 8V1 minus 8V2. This is equation 3. And so at this point, you have done the circuits part, and you now need to do the algebra part. So with simultaneous equations like this, you can do substitution, whatever is easy. What I generally recommend is you go ahead and use your resources, use your calculator, and do some matrix math. So the matrix we're going to set up is, actually we'll do it down here at the bottom. All right, so we're going to be doing an AX equal to B. This is a very standard thing. So this will be a matrix, this will be a vector, and this will be a vector as well. So our A matrix will be 3 by 3. So this will be equation 1, equation 2, and equation 3. The variables in here, this will be V1, V2, and V3. And so for the coefficient in front of the V1, I'll put it here. For the coefficient in front of V2, I'll put it here, blah, blah, so on and so forth. Our X matrix is just our variables. So again, V1, V2, and V3. So the order does matter. It needs to match up with that. And on the right-hand side, this is our constants, if we have them. So we'll go back here to equation 1 and plug in what we have. So for V1, I have 3 of them. For V2, I have -2 of them. And for V3, I have -1 of them. So again, we're describing the coefficients, and our constant is 12. So if you don't want to call that right-hand side, so standard form is to put the constant on the right-hand side. But if you want to, we can just call this constant. So this is our B vector. All right. So I'm going to pause and go ahead and put all the other ones in. All right. So those are all plugged in. So the important thing is just to be able to move all your numbers. So generally, I just move everything over to the left side. So in this case, there's 4 V1s. Then I have -4, and then this will move over, make it -5. This will move over, make it -7. So just make sure you're consistent. For these, there are no constants, so our constants end up being 0. So once we get this, what we want to do is you can, if you have a graphing calculator, you can do this as well. So this is just a Desmos calculator, but we're going to have 3. We need to add a row and add a column, so it's 3 by 3. So we have a 3, a -2, and a -1. So I'll go ahead and finish plugging this in. And then once you're done with that, make a new matrix. So this one will have 3 rows and 1 column, and we're going to have a 12, a 0, and a 0. And then we just do matrix math. And so our matrix math is to find our constants. We're going to do X is equal to A inverse B. So you can plug that in over here. So A inverse times B, and you'll see your answers over here, 4.8, 2.4, and -2.4. And that matches our answers on our sheet. And so those are written down. And so what that means is V1 is 4.8 volts higher than V0, and V3 is actually 2.4 volts lower. So this would actually be, this would actually be our lowest point. So if you actually made this the ground, then all of these nodes would just be 2.4 volts higher. So for example, this would become 0 volts, this would become 2.4 volts, 4.8 volts, and 7.2 volts. So they would all go up by 2.4 if you just changed it. Because again, voltage, or at least node voltage, is based on some common reference point. So in this case, this was our reference point. It didn't happen to be the lowest point on the circuit. We guessed based on this independent source. And generally, that's going to get you pretty close. And it's okay. It's okay to have the negative. You don't actually have to do anything. So we'll leave it that way, with V1 being 4.8, V2, and V3. So this is part of our answer. Once you have solved the circuit, in this case we know every voltage in this circuit, then it wants us to find the current Ix. So the current Ix is here. We've actually written an equation for it. Ix equals V12 over 2, so we don't have to do a whole lot of work. So we know that Ix is equal to V12 over 2. Let me scoot that down for you. If we expand this, it is V1 minus V2 over 2. And it's as easy as plugging in the numbers that we already found. So in this case, V1 being 4.8 and V2 being 2.4. So 4.8 minus 2.4 all over 2. So you're going to get 2.4 over 2, which is going to give you 1.2 amps. And it's positive, which means it is going in the direction of the arrow, as indicated. And you could find all kinds of currents. So you could find the current through this 8 ohm the same way. You would say it's the voltage 2 minus voltage 3 over 8, assuming it goes that direction. So lots of good uses for this. So in this, again, just to recap, we identified our nodes. We wrote KCL equations for each node. We noted that there were 1, 2, 3, 4 nodes. One of them gets to be a reference node, which means that we have 3 left over. So 4 minus 1 is 3. So 3 unknowns means we need 3 equations. We found our 3 equations using KCL and Ohm's law. We plug those into a matrix. There's other ways to solve simultaneous equations. You do not have to use matrix algebra. It just happens to be pretty fast. If you want to, you can look up Cramer's rule. It's a fast way to do this as well. You can solve this matrix C, which is, again, you can use a graphing calculator. You can use it on your test if you want. You'll find your voltages, and then once you find those voltages, you have technically solved the circuit, and you can go find any other quantity in there just using Ohm's law and the known voltages.